Hello students, today we shall start with a new chapter, conservation of momentum, and we shall start this chapter with the topic which is called center of mass. So it is from this chapter that we are going to discuss big bodies and their motion. Till now, till the chapter Newton's laws and work energy power, we were discussing or we were studying only point masses, or at least we were not discussing the extension of the bodies, we were not discussing their size. From this chapter onwards, we are going to discuss the body as the size of the body is, and in order to make the study of such a body simplified, convenient for us, we will consider that point mass which represents the whole body equivalently. So that point in fact is called the center of mass of the body, as the name suggests. I hope you all can understand. Center of mass is that point where the center of the body can be assumed to be placed, right, to be concentrated, or in simple words, the point where all the mass of the body can be assumed to be concentrated is called the center of mass of a body, right. So just to give you an example, let's say we have a disc, a plate like body, like this, okay, like this, a circular plate, let's say. It's a plate, so the mass is distributed over its area. Where do you think we can concentrate all the mass of the plate on this plate itself and say that this point can represent the whole plate as such? Do you all understand? It will be nothing but the center of the mass. If we assume that the mass is distributed uniformly on the area of the plate, it is the center of the plate which will then be the point where we can assume that all the mass of the plate is concentrated, right? So that becomes the center of mass of the plate. Similarly, if we have a rod like body, like this, a rod having a length L, let us say, do you understand that it is the center of the rod where we can assume that all the mass of the rod is concentrated? In fact, if you just keep your finger beneath this point on the rod, you will be able to balance this rod on your finger, isn't it? So that's how we can say that it is this point or this position of the rod which can be considered as the center of the whole mass of the rod. Okay. So in that way, we see that it is the symmetry of the figure that tells us, that gives us an idea about the center of mass of a body. And in fact, understand that the center of mass may not sometimes lie on the body, it might lie outside the body as well. So for example, let's say we have a ring like this. This is a ring now. The above picture was for a disc. For a ring, do you understand that the mass of the ring is distributed over a linear portion, over a curved line, and there is no mass in this central region here? But by symmetry, can we still say that the center of mass of this ring will be at the center of the ring, which will be this point, which ideally does not lie on the ring. There is no mass of the ring at this point, right? But it is, the whole ring is placed symmetrically with respect to this point. So we say that this is the center of mass of the ring. So understand that the center of mass of a body may or may not lie on the body. It might lie outside the body as well. Okay. So in physics, when we try to talk about center of mass of, let's say, two masses, let's say we have two balls. For the sake of convenience, let's take the two balls to be identical, having mass m each. Do you understand where will the center of mass of these two balls as a system lie? We can consider both the balls as a single system, and in that case, do we understand that the center of mass will lie right at the center of the two balls? Over here, we can consider the center of mass of the two balls. In fact, if you attach the two balls with a very light rod, let's say a rod that has no mass, it's a massless rod, then we can hold this system on our finger if we just keep our finger beneath this particular point, the center of mass of this two ball system, right? So in this case, the center of mass lies right in the middle of the two masses if the two masses are identical, because then the distribution of the two masses about the center of mass will be symmetric on the left side as well as on the right side. What will happen in if you have the two masses to be different now? So let's say we have the first ball this time having a mass m1, but the second ball, let's say, has a different mass now, m2. And it is heavier. Let's say m2 is heavier than m1. What do you expect? Do you now expect that the center of mass of this system of two balls will shift towards the mass m2? When you try to balance this system now on your finger, you have to keep your finger somewhere here, a point which is closer to the heavier mass, right? So do we understand from here that the center of mass of a system lies closer to the heavier masses in such a way so that if we mathematically have to look at it, let us consider the two masses to be placed at certain distances on the x-axis. Let's say this is the x-axis on which the two balls are kept. This is the x-axis. Let's say this is the y-axis. And if we have to define some distances, let's say m1 is placed at a distance r1 from the origin. This is the origin here. And m2 is at a distance of r2 from the same origin. The center of the two balls are at distances r1 and r2. In that case, it can be proved, and this is how we define the position of center of mass. We can say that the position of the center of mass, which is this distance RCM, this distance will be defined as m1 r1 plus m2 r2 over m1 plus m2. Okay. For now, since we have taken the two masses along the x-axis, we could have written this as the, in terms of the x coordinate, we could have written x coordinate of center of mass, or the distance x from here, the distance x of the center of mass, xcm will be m1 x1 plus m2 x2 over m1 plus m2. This is the relation. These are the relations that help us identify the position of center of mass in case we are dealing with bodies of different masses. So, for the two balls m1 and m2, we can easily find out the position of center of mass through this. In fact, not just for this system, if we have the masses which are placed anywhere in space, for example, let's say you have the xy plane this time, this is the xy plane, and you have the two masses, let's say the mass m1 which is placed at a position vector r1. Now r1 will be a whole vector, right, in space, and there is another mass m2 which is placed over here. In general, m1 and m2 will be different. So m2 is placed at a position vector r2. In this case, we can still define the position of center of mass RCM with the same formula, m1 r1 plus m2 r2 over m1 plus m2. This is the defining equation for center of mass. Understand that in this case, the center of mass will lie on this line, the line joining the two masses, somewhere over here, depending upon which mass is heavier and which one is lighter. And this is the position of center of mass that we shall get as a vector RCM. Okay. So, in general now, if we have particles placed anywhere in space, we can find out their position of center of masses. In fact, this relation can be extended to more particle system also. Right now, we have just considered two masses. In case we have three particle system, three mass system, the RCM will then become m1 r1 plus m2 r2 plus m3 r3 over m1 plus m2 plus m3. In fact, for n particles, we can write the same expression as, for n particles, the position vector RCM can be written as m1 r1 plus m2 r2, and we go on doing this till we reach the last particle, mn rn divided by m1 plus m2 plus m3 and so on up till mn. Which see that we can write in terms of the summation sign. Do we see that we can write this RCM as summation of mi ri, where I runs from 1 to n. For all the n particles, we are taking the product of the mass and the position vector, and then we are adding all of them up, whole divided by summation of only mi, only the masses are being added now from I is equal to 1 to n. Right? Understand that this expression will give us nothing but the total mass of the body, m1 plus m2 plus m3 on all will give us the total mass of the body. So, we can also write this expression as 1 by capital M, where capital M is the total mass of the body, times summation of mi ri, where I runs from 1 to n. So this expression then becomes a general expression for finding out, let me just write this down again, RCM is equal to 1 by capital M summation Mi Ri, I running from 1 to n. This expression becomes the defining equation for the position of center of mass for an n particle system. Okay. See that this is a vector equation. On the left hand side we have the vector RCM, and on the right hand side we are adding M1, R1, N2, R2, all vectorially are being added, because R being the position vector of different particles is a vector in itself. Do we all understand from our knowledge of vectors that we can split this expression into 3 components along the x, y and the z axis? If we want to write this expression, this can be split in 3 components as XCM is equal to 1 by M summation of Mixi, I running from 1 to n. We need not put the vector sign over the x coordinates now, because we are only dealing along the x axis, so no vector sign required now, right? Similarly, the y coordinate of center of mass will be 1 by capital M summation of Mi Yi, where I runs from 1 to capital N, and similarly z coordinate of center of mass will be 1 by capital M summation of Mi Zi, I running from 1 to capital N. This is how we can find out all the 3 coordinates of the center of mass of a n particle system, a system that consists of n particles, right? You can always reduce it down to 2 or 3 particles, and you can extend it to any number of particles that the body has, right? Now let's observe something. For the same 2 ball system that we considered above, the mass M1 and the mass M2, which is different from M1, let us assume that the center of mass of this system that we have obtained somewhere here, let's say the center of mass lies at the origin. Let's say this is the y axis, this is the x axis, and now this point is the origin itself. So the center of mass of the system of 2 bodies lies at the origin, and let us say the mass M1 is at a distance x1 on the left side of the origin, and the mass M2 is at a distance of x2 from on the right side of the origin. This is these 2 distances. We are discussing the center, the distance from the center of the bodies to the center of mass. In this case, if we use the same formula that we have derived above for the x coordinate of center of mass, which is M1 x1 plus M2 x2 over M1 plus M2, do you understand? If we substitute it here, we will have to use one thing is the x1, the coordinate of the particle M1 is on the left side of the origin. So this x1 will become negative x1. So this will be with a minus sign, because it is to the left side. The coordinate of this point actually will be minus x1 comma 0, isn't it? So this minus sign we have to incorporate in the formula. The second thing is we are getting the center of mass now at the origin. So the x coordinate of the center of mass is actually 0. So this has to be equal to 0. Now what do we understand from here? See that this will give us this M1 plus M2 can be taken on the other side and it will become 0, and we will get minus M1 x1 plus M2 x2 is equal to 0, right? And from there we can get M1 x1 is equal to M2 x2, isn't it so? This is an important relation to understand when we are dealing with the center of mass being kept at the origin, which means that you are measuring all the distances from the center of mass. So when we have 2 masses and you are measuring their distances from the center of mass, the 2 masses will follow this relation. The mass of the body into its distance from the center of mass, the product of the 2 is a constant for both the bodies. This is an important property of the position of the center of mass. This is how the center of mass is placed. In fact, in general, if you have any 2 bodies placed at any position vectors, we can always say that if M1, let's say, is at a distance of R1 from the center of mass and M2 is at a distance of R2 from the same center of mass. Now, they can be placed in any orientation about any axis. This will always be true that M1 R1 will be equal to M2 R2. This is an important relation. We use it directly in questions to solve them. Fine. So far the discussion that we have made on center of mass is for a discrete particle system, when a system is made up of many point particles. So here the mass m1 is a point particle at a position r1, the mass m2 is a point particle at a position r2, and so on, right? Generally we don't study systems like that. Generally our systems are such that they have mass which is continuously distributed over the bodies. So can we say that for a continuous mass distribution, which means that now the masses are not point masses, they are spread everywhere. For example, let's say we have a body, any irregularly shaped body, which is like this. Now the mass is distributed everywhere on the surface of this body, let's say. How do we find out the center of mass of this body? We have to divide this body into many small masses, which we can consider as point masses. Okay, so for example, if we take a small mass over here, this mass has a value of dm1. Why dm1? Because it's a very small mass, just like a point mass. So that's why dm1, a very small mass, which is now at a position vector of r. Okay, r1, let's say. Then we have another mass over here, a small mass only, dm2, which is at a new position vector r2, and so on. Now since we are saying that these masses are very small, how do we cover all the masses of this body and try and find out the center of mass? This is what the situation would be. So what we do is we start with our defining equation for center of mass, which we have written above. It is m1 r1 plus m2 r2 plus so on up till mn rn divided by m1 plus m2 plus m3 and so on up till mn, which we have written as summation of mi ri, where I runs from 1 to n, divided by summation of mi, where I once again runs from 1 to n. Right? Now do you understand, if we want to reduce this formula for a continuous mass distribution, for a continuous mass system, we need to replace our point masses mi, m1, m2, m3 with masses, elemental masses dm1, dm2 and dm3, right? So instead of mi, we will now write dm, a small mass being considered on the body, and the respective position of that mi will be replaced by the respective position of the mass dm that we have taken. So in general, if we have a mass dm over here having a position vector r, can we say that instead of mi we'll write dm, instead of the position vector ri we'll just write r, vector r, which is the position vector of the mass dm, and then instead of adding the terms 1 to n for an n particle system, here when we divide this into very small masses, almost like infinitesimally small masses, which are the masses whose value is approaching 0, because we have, that's the reason why we have written them as dm, isn't it? So can we say we'll get infinite such mass systems? Ideally, when we divide this body into extremely small masses, we'll have to add infinite such masses, right, to get the center of mass. So in order to add up infinite such masses, this summation sign will be replaced by the sign of integration, right? Do we all know from our understanding of integration that integration is nothing but addition of extremely small terms which are very many in number, almost infinite in number, right? That is integration physically. So summation sign will be replaced by the sign of integration, and instead of writing I is equal to 1 to n, we might have to put some limits of integration here, from the lower limit to the upper limit, which will actually depend upon the question in hand, the question that we are solving. But this is how this expression will reduce down to, and the denominator similarly will be written as integral of, summation will be replaced by integral, and mi will be replaced by dm, right? So this expression then becomes our new expression for finding out the position of center of mass of a system, of a continuous mass system, where we divide the system into small masses dm, each having a position r, right? Since it's a small mass, we can consider it to be a point mass, and we can consider the position of that point mass to be given by vector r, and then we can use this integral. Once again, see that integral of dm, which is the sum of all the small masses, will give us nothing but the total mass of the body, so that we can once again write this expression as 1 by capital M, where capital M is the total mass of the body, into integral of dm into vector r, right? So this expression then becomes the defining expression for center of mass of a continuous mass system, 1 by m integral of, I can just write it in this form because generally we keep the integrating factor at the end, right? That's how we generally write an integral, so that's why. Now once again, see that this expression can be expressed in 3 components. We can write this as xcm is equal to 1 by m integral of x dm, ycm is equal to 1 by m integral of y dm, and zcm is equal to 1 by capital M integral of z dm. These are important relations. In the next videos, we will derive relations based upon these formulae for many standard bodies. There are standard expressions that we are supposed to derive for bodies like a half ring and a half disc and a hemisphere and all that. We have done those using these basic definitions of the position of center of mass. Okay, so in the upcoming videos you shall see these derivations that we have done based upon this. So once we have defined the position of center of mass of a system, we can next move on to the finding out the velocity of center of mass. Velocity of center of mass of a system, we can write center of mass in short as COM, right? So what is velocity of center of mass of a system? Once again, just to understand it conveniently, let's take up a system which is made up of 2 masses, okay, mass m1 and m2. Let's say m1 is moving with a velocity v1 and m2 is moving with a velocity v2. Now from the figure we understand that the center of mass will be somewhere here of the 2 particles, and do you understand that as the 2 particles move towards right, the center of mass will also move? So the velocity with which the center of mass of this system of 2 particles move is called the velocity of center of mass. How do we find out the velocity of center of mass if we know the velocity of the 2 bodies? We start with the basic definition of position of center of mass first of all, RCM, which by definition is m1 r1 plus m2 r2 over m1 plus m2, right? And all we need to do now is use the definition of velocity. How do we define velocity? Velocity by definition is the rate of change of position. So delta RCM by delta T. Or we could also use a more refined definition, which is d RCM by dt, the instantaneous rate of change of position of the center of mass. This expression will give us the instantaneous velocity of the center of mass. This expression will give us the average velocity of the center of mass. I hope you all remember from the chapter kinematics what is the difference between these 2 operations. Both of them will give us velocities, but in the first one, since the time interval is delta t, a big time interval, the corresponding change will also be big, and what we'll get will be the average velocity, whereas the other one will give us the instantaneous velocity. For the sake of understanding for now, maybe the basic definitions only, let us just use the above definition, okay, which will work for us for all the cases. So when we use this, can we say using this expression for RCM, we can write this as m1 into delta r1 by delta t. Understand that m1 is a constant. m1 is not going to change, right? So this operator delta by delta t will act on r1. It will not act on m1. So m1 will remain as it is, only delta r1 by delta t, right? Plus similarly m2 into delta r2 by delta t, the rate of change of position of the particle 2, and then divided by m1 plus m2, which will remain as it is because masses are not going to change. So what will this be? This will be nothing but the velocity of the particle 1 v1, and this is nothing but velocity of the second particle v2. So can we say that the velocity of center of mass comes out to be m1 v1 plus m2 v2 over m1 plus m2? Similar to what we have for the position of center of mass, isn't it? So velocity of center of mass, average or instantaneous, whatever it is, you can write it as m1 v1 plus m2 v2 over m1 plus m2. Mind you, this is for a two particle system that we have defined the velocity for center of mass, right? We can as well extend it to a multiple particle system also. Can we write in general for an n particle system, we can write velocity of center of mass as summation of mi vi, where I runs from 1 to n for an n particle system, divided by summation of mi. Same way for an n particle system, this is how we can write the velocity of center of mass. So whatever number of particles you have, you just keep on adding the product of mass with the velocity m1 v1 plus m2 v2 plus m3 v3 plus m4 v4 and so on, divided by m1 plus m2 plus m3 plus so on, total mass. Understand that this can also be written as 1 by capital M times summation of mi vi, because m1 plus m2 plus m3 plus m4 and so on will be nothing but the total mass of the body, right? So see that this expression is very similar to the expression for the position of center of mass. We shall see a little later that this expression has got a lot of applications. But before that, let us also talk about the acceleration of center of mass now. Acceleration of center of mass. So on the same lines, can we say if there are particles which are moving with a certain acceleration also, let's say m1 is moving with an acceleration a1 and m2 is another particle which is moving with an acceleration a2, their center of mass, which can lie anywhere on the line joining them, will also have some acceleration which we can call as ACM, the acceleration of center of mass, which once again can be obtained from the velocity expression. Now can we start with velocity of center of mass as m1 v1 plus m2 v2 over m1 plus m2, and then we can differentiate it. Differentiate as in to find out the acceleration of center of mass. We know that acceleration is nothing but the rate of change of velocity. So it will be dv by dt. I am directly using the differential form now. We could have used delta v by delta t also, but both of them will give us the same result. So this time I am using this one. So this will be nothing but, if we use the value of VCM from here, can we see we will get m1 into dv1 by dt plus m2 into dv2 by dt divided by m1 plus m2, which will be nothing but m1 a1 plus m2 a2 by m1 plus m2. This is what we are getting as the acceleration of center of mass. Once again, an expression similar to what we have obtained for the position of the center of mass as well as for the velocity of the center of mass. All you need to do is multiply the mass with the acceleration individually for all the particles and then add them up. Mind you, it has to be a vector addition. So just in case if you have any of the accelerations opposite to each other or in some other direction, you have to take into consideration those directions. These are vector additions that we are doing here. Can we say in general we can write acceleration of center of mass as 1 by capital M summation of mi ai, where I runs from 1 to n for an n particle system. This will be the general result for acceleration of center of mass, right? So this is how we can find out all the three: the position of center of mass, the velocity of center of mass, as well as the acceleration of center of mass. Now what is the importance? Why are we studying center of mass as such? Let us understand that now. Importance of center of mass. We say that the center of mass of a system is that point which represents the whole body at a single position, at a single point. So that mathematically, one thing is mathematically it is convenient for us to work upon that system in order to study that system, the motion of the system while no, it moves in certain ways. It becomes easy for us if we can just replace the whole big body with a single point mass and study the motion of that point mass itself. Secondly, we say that the Newton's second law that we have studied in the previous chapter. What is Newton's second law? Newton's second law states that F net, the net external force acting on a system is equal to the mass of the system times its acceleration. Isn't this what we have studied for the Newton's second law, right? In case we are studying a system of fixed mass, net force acting on it is equal to the mass into its acceleration. Now, when we use this expression, use the Newton's law for an extended body, a body that has a big size which is not a point mass, we say that this expression is valid only for the center of mass of the body. The acceleration that we obtain from this relation, from the Newton's second law, is for the center of mass of the body. So, for an extended body, we say that the Newton's second law is applicable only on the center of mass of the body. Okay? Which also makes us understand that just in case if the net external force acting on a system is 0, what will happen? Do we understand that this will mean that the acceleration of the center of mass will be 0. Howsoever the other particles of the body move, the center of mass of the body will have a 0 acceleration. Okay? What does this mean? Just to understand this, for example, let's say we have two masses. There is a mass m1 and there is another mass m2. And because of their mutual gravitational attraction, we know that two masses will attract each other through gravitational force. If they exert a force F on each other due to the force of gravity, do we understand they will start moving towards each other under the effect of that force? If there is no other thing hindering their motion, right, they will start moving towards each other. And in this case, if we try to find out the net force on the two particle system, if we consider both the masses as a single system, do we understand that there is no external force on the system? These forces that they are exerting on each other are called internal forces that one part of the system exerts on the other part, right? So these two F's are internal forces. So the net external force on the system is 0, right? Which means that the acceleration of center of mass of the system will also be 0. What does that mean? This means that even though the two particles, the two masses will start moving towards each other, after a certain time they will have some displacement, they will gain some velocity and they will be moving with some acceleration also. But the center of mass of the two bodies, which would be somewhere here in the middle of the two, will not move. It will stay at rest, or at least its acceleration will be 0. So initially if the two masses were at rest, they start from rest. That means initially their center of mass was also at rest. So it will remain at rest at its own position. The two masses might move towards each other, right? So both of them will travel some distances, but the center of mass will not move. It will stay in its position, right? We can check this mathematically also. How do we check it? See, can we use the formula for finding out the acceleration of center of mass in the above case as m1 a1 plus m2 a2 by m1 plus m2? Now look at the figure and see what is the value of a1. a1, which is the acceleration of the mass m1, will be the force acting on it divided by its own mass. F by m1 will be a1. Whereas on the same lines, the acceleration of the mass m2 will be the same F by m2. Also look at the directions. The two forces are acting opposite to each other. The force on the mass capital M is towards right, whereas on m2 it is towards left. Same will be the directions of acceleration. So acceleration of m1 is towards right, whereas of m2 it will be towards left. So when we use these values here in the expression, do you see that we will get m1 into a1, the acceleration of mass m1 is F by m1 towards right, plus m2 into a2, the acceleration of mass m2, which is F by m2 towards left. Now I have to take into consideration the direction because this expression that I have written here is a vector expression, We need to take care of the directions, right? So I'll write the A2 value with a minus sign if I've considered A1 positive, which means that I'm taking rightward direction positive. So any quantity which is pointing towards left will be negative, divided by m1 plus m2. See that m1 cancels out, m2 cancels out, and you're left with f minus f, which is nothing but 0. So you indeed get the acceleration of center of mass of this system to be 0. So though the two particles independently are experiencing some force, they are having some acceleration also, they are moving also, the center of mass does not move because the force is not external. It's all internal force which is creating this motion, right? So what we have understood from here is that if the net external force acting on a system is 0, this means that the acceleration of center of mass of the system is also 0. This is a very, very important result. See next, what do we mean by acceleration of center of mass being 0? Does it not mean that the rate of change of the velocity of center of mass is 0? This is how we define acceleration, isn't it? Acceleration is rate of change of velocity. This will be 0. What do we mean by the rate of change of velocity of center of mass being 0? It means that the velocity of center of mass does not change. Had it been changing, the rate of change wouldn't have been 0. If the rate of change is 0, that means there is no change in the velocity of center of mass, right? So this implies that the velocity of center of mass of this system is a constant. It does not change with time, right? So when we say it is constant, what do we mean by the velocity of center of mass being constant? It means that if the velocity of center of mass is 0, it will remain 0. It remains 0. It does not change, which is the case that we have just taken above in this particular scenario, where the center of mass was initially at rest. It will stay at rest. It will not move anywhere. Whereas if in case initially we have some velocity with the center of mass, velocity of center of mass, if it is not 0, then it will continue to have whatever velocity it has. It remains unchanged, right? This is what it means. There is no change that will happen in the value of the velocity of center of mass in case the external force acting on the system is 0. This is an important result. We get to use it in most of the questions of the chapter conservation of momentum, right? Let's understand this taking an example. Let's say we have two bodies with us. Let's say there is a ball of mass 1 kg and there's another ball of mass 2 kg. Let's say 1 kg ball is moving with a velocity of 2 meters per second and it is coming from behind, and the 2 kg ball, let's say, is at rest. This is at rest. Velocity 0. What do you think will happen here? If the 1 kg ball comes from behind with a certain velocity, after some time it will hit the 2 kg ball, right? So the two balls will collide. This is the concept of collision that we are going to study a little later, but for the sake of taking an example, I'm just discussing it. Do you understand when the two balls collide, that means they will exert some forces on each other? Both of them will exert some force during the course of collision, because of which they will undergo a change in their state. The one which is moving might come at rest, and the one which is at rest initially might start moving. So let us take such an example. Let us assume that after the collision, the 1 kg ball stops. The velocity of the 1 kg ball becomes 0 after the collision. We are supposed to find out the velocity of the 2 kg ball after collision. This is what we are supposed to find out. Now, do we understand that during the course of collision, no external force came and acted on the system of two balls? The two balls exerted some force of impact on each other, but those forces will be internal forces. They will be equal and opposite by Newton's third law. And if we consider the whole system, these forces will always cancel out. Equal and opposite forces, anyway they are internal forces, right? These are not external forces. So can we say, since the net external force on this system is 0, the acceleration of center of mass will be 0. That means the velocity of the center of mass will remain constant. That means the velocity of center of mass initially will be equal to the velocity of center of mass finally for the system. Before collision and after collision, the velocity of center of mass will remain the same. What is the velocity of center of mass of the system initially? m1, the mass 1 kg into initial velocity 2, plus the second mass m2 v2, 2 kg mass with the initial velocity of 0 divided by m1 plus m2. Okay, m1 plus m2 means 1 plus 2, 1 kg plus 2 kg. So what do we get here? We get 2 by 3 meters per second as the initial velocity of the center of mass. What is the final velocity of center of mass according to the figure that we have drawn? m1 v1 is 1 into 0 plus m2 v2 is 2 into v. We are assuming the velocity of 2 kg ball as v divided by m1 plus m2. So this is 2v by 3 meters per second. Can we now say that since these two have to be equal, 2v by 3 should be equal to 2 by 3, and that gives us v is equal to 1 meter per second as the velocity of the ball of mass 2 kg. Right? So by using this concept we can solve such questions. So this is an important aspect that we have understood just now. When the net external force acting on a system is 0, its velocity of center of mass does not change with time, it remains the same. What if there is a net external force? What if the net external force is not 0? Net external force is non-zero. If this is the case, can we say from here, we can say that the net external force will be equal to the mass into the acceleration of the center of mass, right? Which tells us that the acceleration of center of mass will be nothing but the force, net external force coming and acting on the system divided by the total mass of the system, which is an equation which is similar to the equation A is equal to F by m that we studied in the chapter Newton's laws of motion for a single particle. When there is a force F acting on a single particle, it has an acceleration of A. Here what we are getting is, if there is a net external force acting on a system of particles, then the acceleration of the center of mass of those particles will be the same, will follow the same motion as followed by a single particle on which the same force F acts, right? So in that sense we understand that the center of mass behaves as that single point. No, if we can just replace the whole an n particle system with one single point and exert all the force that is acting on the n particles on this one single point, it will undergo the same type of motion as a single point would have undergone under the effect of the same force, right? So once again we understand that center of mass in that sense simplifies our study of a multiple particle system or an extended system, a system which is not small, which is not moving as easily, like in a simpler way. The one which has a complex motion, we can simplify the motion by considering only the motion of the center of mass of the system. Just to give you an example, let's say we have studied projectile motion in the chapter kinematics, right? There we saw that when we project a projectile like this, there is a mass that we project, it undergoes a path like this, a projectile motion, right? Now let us assume that there is this body that we have projected from here of a certain mass, and as it reaches somewhere on its path, let's say when it reaches over here, it breaks into two parts. This was a big body, it could have broken due to some reason. When it breaks into two parts, let's say one particle that breaks out goes in a path like this, anyway it will go, and the second particle that it breaks into goes in a path like this. Okay, now understand that essentially the motion of these two particles now will be a little complex, because in order to find out where exactly these two particles went, we need to know everything about this state where the explosion happened, where this particle exploded into two particles. But do you understand that by using the concept of center of mass, we can still say that since on this particle which got exploded, the only external force acting was its weight, the mg force, which is usually the case for a projectile. Do we understand that if we consider the center of mass of these two particles, the center of mass, which is that one single point that can represent the two masses together, can we say that the center of mass of these two particles will still follow the same original path that the body would have followed had it not exploded? So this will be the path of the center of mass. The center of mass will still land at the same position on the ground where the original particle would have landed. At any point in time, the velocity of the center of mass will be the same as that of the original particle's velocity would have been had it not exploded, and everything would be the same. So we can actually reduce this two particle motion into the motion of its center of mass. So we can in fact say that if we know the position of one of the particles, where the one particle, let's say number 1 particle, lands here on the ground, can we find out where the particle 2 will land on the ground? We can, if we know the position of center of mass. Do we know that the center of mass will still follow the original path and it will land on the ground where our actual original particle would have landed, which is nothing but the distance r, the horizontal range, right? If we know that, and if we also know the position of particle number 1, let's say, then by using the definition of position of center of mass, can we find out the position of the second particle? Yes. We shall see that questions like this are asked in this particular chapter, and they are quite interesting. They make the working of the question quite simple if you just use the concept of center of mass. Okay. So in the upcoming videos, we shall talk about a very important law which is based upon the concept of center of mass, which we call as the law of conservation of momentum. We shall see how using that law we can solve almost all the problems which contain many particles having some complex motions, but they are moving without any external force acting on them, and then we see that how by using the concept of center of mass it becomes quite easy for us to discuss all their motion.